Cars today implement a variety of onboard electronic systems that aid the driver in making safe driving decisions. However, if the driver fails to use them properly, or relies too heavily on these systems, the effectiveness of the technology and the safety of the driver can be compromised. To address this, our goal was to determine if we can estimate a driver's stress levels, data which could be used to develop intelligent systems that better support the driver. For example, automatic stress detection could be used to trigger driver support systems before the driver realizes they need them. For our project, we designed and executed an experiment to find and test a group of consumer wearables currently on the market for their potential in detecting stress while driving. We first determined the biometrics we wanted to measure, heart rate and heart rate variability, in order to measure the subject's stress. From there, we selected consumer wearables which could measure these signals. We chose the Garmin Forerunner 55, Google Pixel Watch, Whoop Band, and Oura Ring as our wearables to test. In addition, we used a Bidelino, an industry-grade ECG device, to take our control measurements, as well as a proprietary headset sent directly by Nissan. For our experiment, we had two phases. In phase 1, we recruited 20 participants to test their mental agility and assess how prone to stress they are via stress questionnaires and a Stroop test. In phase 2, we selected 15 of these participants to use our driving simulator while we recorded their biosignals. During phase 2, our participants were equipped with all of our wearable devices and drove under two scenarios. They first drove in a low-stress environment, where they were simply asked to drive safely at a comfortable speed to get low-stress readings. In the second scenario, the participants were asked to closely follow a car and were verbally reminded to stay in range in order to induce moderate to high stress. They completed 2 low and 2 high stress rounds, lasting 10 minutes each, and measurements were collected by all devices in this time for our analysis. We started our data analysis by investigating if the signals from high stress and low stress rounds appeared different. In this figure, we have averaged all participant data for the first high stress and second low stress round. These rounds were chosen because they had the highest and lowest self-reported stress scores, respectively. The top row shows the average signal across participants, and the bottom shows the standard deviation. When looking at the top row, we see a separation between the rounds for the Pixel and Whoop heart rate and Garmin heart rate variability signal. This shows the promise that a machine learning decoder could predict whether a participant was stressed or not. However, the standard deviations for these signals are quite high. We attribute this to the fact that the data is not averaged from moments where the participants are doing the exact same driving maneuvers. Since each participant drove at different speeds, there will naturally be some variation due to the different positions on the track. We have not plotted Oura Ring data because the ring did not report data in the unguided meditation mode, which was the only mode in which it would record heart rate and heart rate variability data. Now, draw your attention to the top right plot. We see that the Garmin's heart rate variability signal is higher in high stress rounds as compared to low stress rounds. This is contrary to what literature says should happen. While the separation of the signals is clear, more work should be done to investigate the Garmin's heart rate variability calculation. Now, let's move on to the headrest. While performing the experiment, we noticed that as a participant drove, the headrest signals would have larger amplitudes when one of us would move around the room. We believed that these artifacts would corrupt the signal. The plot in this slide lends some credence to this claim. Here, we calculated the Pearson's correlation coefficient between the headrest alpha signal and the Bidelino heart rate, using a non-overlapping 10-second window for one participant. We would expect these signals to be strongly correlated, as the headrest should reflect the same physiological changes represented by the Bidelino. However, the correlation is not consistent over time, and as a result, we believe that the headrest may not be predictive of stress. While there was more analysis we would have liked to do, we ran out of time, so let's move on to the conclusions. We found that the Garmin, Pixel, and Whoop wearables were all promising for stress detection. In contrast, we are less confident about the headrest and Oura Ring's ability to detect stress. The next steps include training a machine learning model to see if stress can be predicted from the promising devices. We also believe that some changes can be made to the experiment setup, namely creating systems for more accurate timing so that more precise grained averages can be calculated. Thank you for watching.